Hello and welcome. In today's session, we will show you how you can accelerate automotive ADAS validation with hardware-in-the-loop testing. For that, we first of all have to have a look onto what the current situation in radar-based autonomous driving is. And the current situation basically looks like that. There are more and more safety-relevant autonomous driving features implemented in each car. And most of those features rely on radar sensors. So for example, we have cross-traffic assistance, we have autonomous emergency braking systems, and also rear collision warning systems. And all those systems need to be tested when we talk about certification and validation of new vehicles, or if, let's say, a new software version or firmware version is installed onto the radar sensor. So what are the test challenges that we currently face, and what is the initial situation when we talk about radar-based hardware-in-the-loop testing? So the current capabilities of closed-loop test systems are that real-time simulation allows the complete testing of embedded software running on the ADAS ECU itself or on the radar sensor under test, whether it's a more, let's say, basic system. It also provides a very good standardized test coverage. What does that mean? So let's say you have a test catalog like Euro NCAP, for example, and you can test or validate the radar sensor's functionality before even going to a proving ground with a vehicle where the radar sensor is installed in. Further, there is a very high variability of test cases. And also there is a very high capability of parameterizing scenarios. So it can be automatically changed in some parameters and therefore perform adjustments to certain predefined scenarios. And last but not least, as a further important factor, test cases include validation of the whole ECU firmware and even the whole operating system that is the foundation for the ADAS function. But we are also facing challenges there. And one of the challenges is that we have a limitation of the current laboratory test options. So we have limited scenario testing capabilities due to the hardware, the echo generators that were available until now. So we will show you a solution, of course, later on where we face those test challenges. Then there is the lack of azimuthal moving targets, which are very challenging to simulate in the lab. And there is often just the scenario-based open and closed loop testing capability missing. And last but not least, which will be today a major point, is that there is a lack of an open interface that allows an easy connection of hardware into hardware-in-the-loop applications. So the test equipment itself needs an easy and convenient way to be integrated into sophisticated hardware-in-the-loop test systems. And that's also something that we want to show you and introduce to you today. But first, let's have a look on the variety of driving scenarios and driving situations that a capable hardware-in-the-loop test system must be able to address. And we start with a very simple situation, let's say. So we have an obstacle, an object that is crossing the road, and just a single one, like it's defined by the Euro NCAP test cases and what is necessary for autonomous emergency braking and also ACC scenario testing. These scenarios need a simulation of targets with which are moving in azimuth, in range, in radial velocity, and also in target size. And this sort of basic test setup, test system is typically capable of stimulating a single radar sensor under test. We have at Rohde & Schwarz the ideal solution for that scenario. So with the ARIC 800A radar echo generator and the QAT100 advanced antenna array, you can very easily and convenient reproduce this sort of scenarios in the lab. So for example, the driving situation as is shown here, with a car coming to a crossroad and where an autonomous emergency braking in the end should be triggered, can be very easily and convenient addressed. Typically, it's not only limited to those sort of, let's say, basic driving situations. Most of the time, more advanced and complex scenarios are required. And of course, the ARIC 800A and the QAT100 are also capable of addressing these scenarios. So we have the same, let's say, foundation. So we can simulate targets moving in azimuth, in range, in radial velocity, and also in target size. But now it's often required that, for example, multiple radar sensors are stimulated in a synchronous manner. And that's something that we can address also with our setup by, let's say, adding, for example, more QAT100, more advanced antenna array front ends to a single ARIC 800A backend. And for example, that situation that is shown here, where a car is moving or driving onto a highway, the car has two radar sensors installed, one long-range sensor in the front and one corner radar sensor on the left side. And both radar sensors either see targets at the same point in time and therefore need to be stimulated in a synchronous manner, or the targets, let's say, move into the first radar sensor's field of view and then leave it and move on into the field of view of the second radar sensor. And with the QAT and ARIC 800A, you can easily address that. So, but now let's talk more about how closed loop validation works with the ARIC 800 and the QAT100, and how radar sensors and underlying ADAS and AD functions are tested with those instruments. So and as mentioned before, the whole foundation for those test cases where safety critical ADAS functions should be tested is the echo generator ARIC 800 together with the QAT100. I already teased a few parameters or scenarios that the ARIC 800 can address, but I just want to give you a short overview what is capable with a system of those two instruments. So we have here a performance optimized system. So ARIC 800 and QAT100 are developed hand in hand and are perfectly aligned onto each other. So they are working as one setup. It's not like there are two separate boxes. They both work as one setup. You can generate multiple independent objects. That means you can also generate more complex driving scenarios, not only the basic scenarios. And as shown before, you can scale the system up. So you can, for example, if you want to extend the field of view, where you want to be able to generate artificial objects, or if you want to test more than just one radar sensor at one point in time, you can add more QAT100 advanced antenna arrays. On the other hand, if you want to have more objects, so you want to have the possibility to generate more objects than one ARIC 800A is capable of delivering, then you can also scale up the ARIC 800s and therefore add more artificial objects to the whole setup. Of course, everything in that case is synchronized, so you do not have to take care about synchronization there, and the scenario is streamed into the instruments using our built-in real-time interface. And how does that streaming work? We have a seamless integration of that built-in real-time interface using the Open Simulation interface, where we have a closer look later on to. So, but before we go more into hardware in the loop testing, I want to give you an idea what's also capable with the instruments, and that is, for example, vehicle in the loop testing. So if you have a new vehicle, a new platform with a new ADAS AD functionality implemented, you want to validate at the end of the day whether the whole vehicle as a system is working as intended, and you want to perform therefore black box tests with the car. So where no connection or whatsoever is between the test system and the car under test. And therefore, we have a great solution together with a partner of us, with AVL, which is one of the largest providers of roller test beds in the world. And we implemented together a solution for vehicle in the loop validation of whole cars, whole vehicles. How does it work in that way? So we have on the one hand side, on the left side, you can see the AVL software suite, which provides you an interface to the whole mechanical stimulation, so to the roller dynos, to the wheel stimulation, and which also provides you the possibility to generate a virtual driving environment. And from that virtual driving environment, object parameters are extracted and put into a parameter list that exactly match that driving environment. And that extracted parameter list is then streamed into the AREC 800A, and the AREC in the end then over the air stimulates using the QAT100 the radar sensor under test. And therefore, one can say the vehicle as whole system is under test and not only the radar sensor. Beside radar, of course, you can add further stimulation to a setup like this. For example, you can also stimulate the GNSS receiver and also, for example, the CV2X interfaces, also in a synchronized manner to the radar sensor. Okay, but not only vehicle in the loop is important, what's also very important in the step before is validating the automotive radar sensors using realistic hardware in the loop scenarios already in the lab before the sensor is installed onto the car. And therefore, we provide you a solution for hardware in the loop testing. So you can use as a software, a simulation environment, for example, Dyna4 from Vector, and a ResBus simulation and result validation software that interact with each other and share the driving scenario data. The environment or the actual driving situation is generated by Dyna4, and basically the same as with a vehicle in the loop. The parameters for the radar objects is extracted from the driving situation and therefore then stored into an object description which contains the basic parameters. In the next step, we add more or less our hardware. So the AREC 800 and the QAT100. The AREC 800 is connected to that software package using the open simulation interface. The AREC then remote controls the QAT, takes over the object description from the environment simulation software, the extracted parameter list, and then over the air stimulates the radar sensor under test with it. And as soon as the radar sensor under test then detects the scenario, we close the loop. So we feed back the object list data that is outputted from the radar sensor under test to the ResBus simulation software, which can be Canoe, for example, or the result validation software, and therefore then have the whole loop closed. But what is the most important step in that case? Or what is the most important interface in that case that allows you to generate that closed loop situation in an easy and convenient way. And that's for sure is the interface between software and hardware, which in the end enables you to run hardware in the loop testing. And that is the open simulation interface where we want to continue now with. And therefore I have my colleague here in the studio, and he will explain you the benefits and how we implemented open simulation interface in the ARIC 800.
Yeah, thank you, Alois, for a short introduction. So I'm from the development team of the ARIC 800A and was responsible for the integration of a hardware in the loop interface. So, and in the end, we decided for the open simulation interface, and this is why I want to show you in the first place what it actually is and how it's integrated into our software and how you can use it on your own. So, the open simulation interface basically is only the specification of interfaces between different models and components involved in a distributed simulation. So in this case, it's specialized on automotive applications and the perception of automotive driving applications. And therefore, the open simulation interface offers different descriptions in a high-level language. So it's called the Google Protocol Buffers, which gives you a platform-independent description for different parameters and messages. So here in the slide, I have shown you an example of that. So you have the environment simulation, which is responsible for generating the whole scenario and moving objects and something like this. And from this, there's generated an OSI message, the sensor view. And the sensor view basically gives the sensor models all the information they need to generate their data. And the sensor model decides, depending on its own parameters, which objects can be seen at what time, and gives that to a ADAS function. In this case, this is what we want to see. So the ARIC 800A needs the information which objects he has to generate at what time. So now I'll show you a little bit more. So in our case, the key parameters of each object is the range of the object in front of the sensor, the relative velocity, as well as the direction and the size in terms of the radar cross-section. So, and also included in the open simulation interface is the serializer. So the serializer basically can generate a binary data block for all different programming languages and stuff like this. So you can transmit it via a network interface or basically just write it to a file. And this is what we do in the ARIC 800A. So if you have on the one hand the hardware in the loop interface, you can transmit these data, these serialized data packets to the ARIC 800A. And then we know which kind of objects with which parameters we have to generate. On the other hand, if you want to generate some reproducible scenarios for different test cases, you can also write it to a file and play it over and over again and test always the same stuff. So this was a little bit abstract. I want to show you exactly how the messages are built up that we use. So basically we use OSI sensor data, as I mentioned before, which includes different kinds of parameters. So on the one hand, you have, for reasons of reproducibility, you have the interface version. So if the interface changes, we know how to handle that. So if a parameter, the unit or the orientation has changed. So on the other hand, you get a sensor ID. And this is pretty important because this also enables that we stimulate multiple sensors at the same time. So each sensor model gets its own sensor view data and can generate the objects we have to generate from this. And additionally, there's the timestamp. So the timestamp basically says at what point of time in simulation time this object list is valid for us. And included in this data packet, so it's a nested structure, and inside there's for each object we want to generate is a radar detection included. And to make it more visible for you, I added some of the descriptions from the documentation of the open simulation interface. So there's exactly said that which parameter is in which unit. So then it's a convenient way to integrate all the different simulation environments. So you don't have to change it all the time, and the one needs the one unit, the other one needs the other unit for the parameter. And the other parameter I want to show you is the position, because the important point is it's specified in which coordinate system you have to generate your objects, or the object data is presented to us. So we can use it and reproduce the scenario generated from the 3D simulation. Okay, so this was basically a short introduction on what the open simulation interface is. And now I really want to show you how you can work with our device to integrate it into your solution. So on this slide, you can see the graphical user interface of the ARIC 800A. So in order to generate your scenario, you first of all have to give us some information. So basically, you have your hardware setup standing right in front of you, and you know where it is and how you place it in front of your car, in front of your sensor. And this is why you have to configure which front ends are connected. For example, here for the QRT 100, you have some parameters like the air gap in this slide here. You can tell us what's the distance between the sensor and the RF front end. There are some other parameters, the angle it's placed and which frequency band it's working on and stuff like this. So this is the first step. And in the second step, you also have to configure which radar sensors are involved. So this is because you can have different radar sensors, different radar bands, and bring it all together. So the 3D simulation software doesn't have to know anything about the hardware. Only our device has to. And then this is what we do in the third step. So you take it all together, map it in a small way, and then we are set up for the simulation. And in the final step, you can just verify if you've done everything right, if your setup is okay with this preview dialog or the overview dialog. And this shows you in which angle and which distance you can simulate the object. So I think this is a pretty convenient way to check if it's all right, if you can generate your scenario and stuff like this. Okay, so and then basically everything is set up and we can start simulating or with the simulation. And as mentioned before, there are two different objects. On the one hand, you can either stream it directly via network interface. So we provide different protocols for this. For example, a simple UDP. And then you stream the data to the device. And yeah, that's basically it. And the other way is that, as I mentioned before, the scenario mode, where you write all the open simulation interface packages just to a file, and you can play it over and over again, even play it in a loop. And now the scenario is running, and then you still have different ways of verifying that you're doing the thing you want to do during the scenario runtime. So we provided different opportunities for this. So on the one hand, you already saw the visual overview. So if the scenario is running, you also get the information where are the objects you're currently simulating. To get an even more detailed knowledge of what we're doing right now, you can also see such a table overview where all the other parameters that are not visible so easily, like the Doppler shift or the radar cross section, are also included. So basically, this is a list representation of the first dialog. And at least, we also have a list of events that are happening. And so basically here, what you can see when the scenario restarted, when there are different objects you couldn't map on the hardware, something like this. And this can also be represented on the time of your scenario. So in the open simulation interface, timestamps are included, and you know exactly at what time of the simulation the problem occurred, and you can fix it and generate a new scenario file and play it again. So this was basically it. So I would hand over back to Alois.
Thank you. So now that we have learned how we implemented the open simulation interface in the ARIC 800 and in our hardware in the loop setup, as well as we have seen what the open simulation interface actually is and how it is defined, we now want to have a look at an exemplary driving situation where you can see how the actual implementation works. And therefore, we have that scenario here. So it's basically the same as before. Now we have a simulation environment, Dyna 4, running in the background, and we also have Canoe up and running as RESPA simulation software. And the software suite is connected to the AREC 800 using or utilizing the open simulation interface connection. And yeah, what you see in the actual video is the scenario editor running in Dyna 4 with a driving situation where a car is overtaking a truck and where the actual objects are streamed using the hardware in the loop interface to the AREC 800A and then visualized. So let's sum up what we have seen today. We showed you today how you can easily and in a convenient way integrate the AREC 800 and QAT 100 into a hardware in the loop setup using the open simulation interface, which is great because it's completely open. You can have a close look into the documentation and easily adapt it into your test system. With the AREC 800 and the QAT 100, we have a very flexible and scalable solution for addressing hardware in the loop and also scenario-based test cases where you can add or remove instruments, so backends, AREC 800s or QAT 100s to your setup as you need. And of course, thanks to the QAT 100 and the advanced antenna array approach, we have very precise and repeatable measurements thanks to the electronic realization of the azimuth angle. So thank you for joining today and see you next time.